computer networking. This is part 4, where we're going to take a look at both UDP and TCP from an application programmer's perspective. What I have here, first of all, is the source code for UDP-based client that will send messages back and forth between itself and another UDP server. I'll post this code up to the D2L site so that you can really take a look at it as you like. The idea is that this client has to be told where the server is, and we're going to do that with its IP address and a port number. And the server's information is only one part of the minimum amount of information that I need to open a connection. I also need to have a local IP address and a local port number. And by definition, they'll be different. So the addresses might be the same, but then the port numbers have to be different. So to connect everything together, what I've done is I've created this struct that you see here from lines 28 to 39 that hold all of the information that the client keeps track about itself. So what IP address has it open, what port number is it trying to connect to, what's the local address it's using, what's the remote address that it's trying to use. And then we're going to see that once we have all that information, we can create a socket in the operating system that allows this application to communicate with the operating system. A lot of times when we look at socket programming, we think about sockets in the operating system as the virtual circuit between my machine and your machine. But in this case, the socket is really just this application having a communications channel to the operating system for when I want to send data to the remote site, or for the remote site to get data back into my program. But it's important to know that UDP is a connectionless protocol. It doesn't actually maintain a connection between the two operating systems. This is just a convenience. The socket here is just a convenience for the local operating system in my application to communicate back and forth. I have some helper routines that initialize the local address part of the client and the remote address part of the client. We see here that I'm using the internet address family, and I'm using the port numbers that the application has picked. I'm also using a special function called inet underscore a to n, which is going to convert an ASCII address of an internet address to a numeric internet address. So in fact, if I hover over it, it even says that. So in this case, it's going to be able to take the address of 127.0.0.1 and turn it into an integer, that 32-bit IP address that we use for IP of version 4. The next layer up from those two helper functions is this client connect function. You pass it in a client object or client struct, and it sets the local or remote addresses. It creates that socket between my program and the operating system, and I'm going to tell it that I want to use the internet and I want to use datagram, which is its way of saying UDP. And if the operating system says, sure, you can have that socket, then it will return a number greater than or equal to 0. On the other hand, if it says, no, you can't have that socket, I'll get a negative number, and then I know that the program is borked and I need to exit. The next thing I need to do is to tell the operating system to bind my socket to those addresses so that whenever I send data, it should be using this information. And so what's going to happen here in bind is the client's going to ask the operating system, hey man, I want to communicate on this channel. What local port number should I use? Because remember, we gave it 0 before. And this will allow the operating system to pick from any of the 65,535 different port numbers that it could use which one it wants to give you. And so that's what bind is going to do. And then finally, I do the actual data exchange. And this one's really simple. We pass in the client, and then the data we want to send, and then a place to stuff the data that we receive. I'm going to use a pair of functions, send to and receive from, that are going to be able to send data out to the server and receive data back from the server. And then finally, main. Main comes in here. We're going to initialize that client struct and connect to it. And then I'm going to call client exchange to send the message hello from client to the server, and then read whatever the server gave me up to 128 bytes, and then print that message and then exit. So in this terminal window, I'm going to go ahead and run the server. I know we haven't actually looked at the code yet. That's fine. But let's do the client. So if I go ahead and run the client, I get this message that comes back and says, hello from server. I'm getting some garbage there. I'm getting garbage because of that. This needs to be... No? Yeah, that's kind of strange. Why am I getting garbage there all of a sudden? I wonder if I'm not... Oh, I'm not zeroing out from server. So if I do a memset from server 0 size of from server. So I think what's happening is the server message comes in and it ends, but then there's some garbage at the end of that string. By zeroing out the whole buffer, yay, look at that. By zeroing out the whole buffer, I was able to have a null at the end of that line for a null, null terminated string. Pretty common mistake to make. Phenomenal. So there's the client. Let's take a look. The server, by the way, the server got its message. It says from client, hello from client. Not terribly useful. Over here is the server code, and what we're going to see is the server listens on a port number, same port number that we used over here in UDP client. So we'll see 4321 here in the client, and if I go back to the server, we see 4321 here in the server. Only this time when I create the socket, I'm still going to do AFINet and I'm still going to do a datagram. I'm still going to do a bind to get a local port number, but this time the port number is going to be bound to the port number that I'm supposed to be listening on, this 4321. And because this is a connectionless protocol, UDP, I can literally just go ahead and start receiving or sending messages. Like there's no connection handshake like what we're going to see when we look at TCP. So in the case of receive from, I'm going to receive from just about any host in the entire universe. And then we're going to send data back to whoever sent us data. And so we're going to send the string that says hello from server. And in the meantime, we're going to exit or return. So the server fills in those values and then it just prints out the message. And then we sit in an infinite while loop. So I can keep on doing UDP client and see hello from client and get the server back saying hello from server. A little off-camera action, and what I've been able to do is to run the UDP server under Cygwin under my Windows machine. And so now if I go back to that ifconfig, this machine is 172.27150.231. My Windows machine, I have to do a little bit more work. It becomes IP config for some reason under Windows. Who knows? So the Windows side of my Windows services for Linux is 172.27144.1. So what I need to do next is edit. Sorry, this is really gnarly, but it's a good kind of overview of some of the weird things that we end up having to do. So it is on the Windows side 172.27144.1. 172.144.1. And in fact, I should be able to ping that address. So ping 172, gotta remember the number, 27144.1. And I can. So the Windows machine is listening on that IP address. And in fact, if I find Wireshark, did I kill Wireshark? I must have killed Wireshark. If I go back to Wireshark and I listen in on that adapter, I can see my ping packets going back and forth. So I know that my two computers are talking. And when you're trying to help an application developer understand whether their application is working, being able to ping is really, really crucial because it can give you an idea of the round trip time and whether or not the data is getting there and being lost along the way, or whether there's a whole round trip that can be made. Wireshark lets you see both the request and the reply. So it's really nice to be able to see that there is connection happening. So I'm going to go ahead and do this one more time. We've modified the code. And I could swear that the server was running. Oh, wrong client, wrong window. So let's run that again and let's see what Wireshark shows. Nothing. Did I not save this file? I'm in the wrong, oh, stupid me, I'm in the wrong file. I need to be in the UDP client. And then we do a make. And now what does Wireshark show? So Wireshark shows, let me stop. So Wireshark shows that my computer on local port number 36,000 sent out a message that said hello from client to my Windows machine on port 4321, but then there was no response at all. So if I go back to here, that makes sense. I'm not running the program. So let's run UDP server. So now UDP server is running. And we got a full round trip. Oh, but I wasn't running Wireshark. Oh. So we'll do it again. Boom. And we'll sit back over here and hit stop. And so there's the message. So our first message happens at from 172.27150 to whatever over the UDP protocol. 18 bytes got sent, hello from client. And then the reply came from that machine to my local machine from port 4321 to port 42360. Hello from server. They just happen to be the same length. So there we can actually see Wireshark allowing us to look at the conversation that goes on between these two. And in fact, we should be able to look at this and so there we can analyze, and I want to see it just as a conversation. There. So based on this, we can actually use this to see the conversation between these two machines and what's going back and forth between them. So kind of neat that we can do Wireshark and see that level of activity. All right. So there is the UDP client. Again, I'll post the UDP client and the server up to the DDL site, where we'll take a look at using the TCP API to do almost exactly the same thing. So this is the TCP client. I've already got the right port number in. The setup for the TCP client is going to be a little bit more tricky than it was for the UDP, just because TCP actually establishes a connection that lingers back and forth between them. So in this case, we're going to do the same, set up a remote address. We're going to do the same, open up a socket between my program and the operating system. But this time, instead of saying sock underscore dgram for UDP, we're going to do sock underscore stream for TCP, the other transport protocol that's available to applications. And then I'm going to ask the operating system to go ahead and get connected. And in this case, we'll actually try to do a demo of this, but if the connection can't be made, we'll know that, we'll fail. So this is right away one of the big differences between TCP and UDP. TCP is reliable and will tell us if it can't deliver the messages that we ask it to, or it can't establish the connection in this case. So we'll be able to see that work. Likewise here, when we want to do a client exchange, instead of doing a send to, where I have to send the address to the machine that I want to send it to and then tell the operating system where I want to receive it from, because the socket is fully connected and it actually is connected from my application to the operating system to the remote operating system directly to the remote application, I can just use read and writes on the socket file descriptor just like we would if these were files. So using TCP gets me a little bit closer to treating the remote machine like it was just a file on my local machine, which is really kind of neat. Finally, the client setup is the same. The message exchange is going to be the same. The output should be the same. Let's take a look at the server really quickly. Same kind of overview as we saw before. We're going to listen on the same port number. We're going to initialize the same set of addresses. Only in this case, what I'm telling the operating system is, what machines do I want to listen for, like incoming connections from? I want to listen for anything. So in, adder, any. Let me listen on the whole wide world. And then we're going to do bind. And we saw bind show up before in the UDP version. This case, we're going to be binding the socket to the server address. This still doesn't actually turn this into a server. Bind is just saying this socket ID is connected to that address. The magic that makes the TCP server a TCP server is that call to this function called listen. And whenever I call listen, listen's going to just sit and wait for a connection to come in play and a connection to come in. And once the connection's been made, then the socket will be connected and I can read and write from it. So this is going to tell the Unix operating system that I want to listen for connections, and this tells the Unix operating system that I'm ready to accept a connection. And what's really weird about this is where we used the socket that we created to actually send data in UDP, I used the socket that I created to communicate with as a client. That was fine. But here in the server, I used the socket to communicate to the operating system's abstraction of a listening server. So the sockfd is really talking about the server socket. And when I call accept, the accept system call is going to sit and wait until somebody knocks on my front door. And once I've established the protocol and let them in, it makes another socket. And I get a file ID for that socket. In this case, it's called client FD. And then we'll see in a minute that we use the client FD and server exchange. But the server exchange looks just like the other one did. We're going to read and we're going to write, right? So here we call server setup to set up that server socket and tell it we're going to listen for incoming connections and we're just going to kind of hang out. And then here, this is where I tell it to listen. And then here, I'm going to wait for somebody to ring the doorbell and say, I want to exchange data with you. And I'm going to get a client socket for that connection. And then what we're going to do is we're going to do the server exchange. We're going to print the message. We're going to close that client connection and then get ready to listen for some more data. Now, again, this is listening on any machine. And I've already made our TCP client communicate to my Windows machine. We'll do a make clean and a make. We'll run the TCP server .exe. The Windows firewall says, dude, do you really want to let this program listen for incoming connections? And I say, absolutely, because I'm sure that's safe. And so back under Linux, now I can do my client. And we see our message, hello from server. This time what I want to do is I'm going to bring up Wireshark again. And we're going to go ahead and start capturing data. And this time you see that we are using TCP. And there's a bunch more stuff. Like TCP exchanges a lot more messages when it sets up a connection. look into like a deep dive into the sockets API that's built into Linux. My experience with software engineers, and again, I don't mean to denigrate software engineers, but they're typically happy to get their data and go on with the rest of their processing, and they don't really want to do a deep dive into creating sockets and the interaction with the operating system. Like that doesn't typically excite them. Maybe it does. And like I said, I don't mean to pick on software engineers in particular. But the operating system provides this socket API. And when we learn about the different protocols like TCP and UDP, we're going to see that there's all kinds of options for headers and sending urgent messages or push messages or all kinds of crazy things. And by and large, the operating systems today do a pretty good job of kind of like the default is right attitude of it's okay. But sometimes you get into an application and the software developer is going to come to you and say, man, this application needs to work. And we're really stuck with the network. Like sending data out is just not getting there in a timely way. It's throwing all kinds of errors. And the first thing we might want to do is bring up Wireshark. Like that's your first inclination. And that can help diagnose the error, but you're going to end up having to help the user, the programmer, fix that problem. And the chief way that you're going to do this is you're going to look at what's going on in Wireshark and find out what's happening, and you're going to see that there's some kind of a misconfiguration. And you're either going to end up having to work with the systems administrator to change the configuration of the operating system for that application, or you're going to work with the software developer to change how they're using the sockets layer. So far, we've seen the socket creation function, and the socket inet function that we just talked about is the internet function. But look, there's two other socket types. One of them is to use the old NetWare IPX SPX protocol, which typically isn't used anywhere anymore. Although it could be a really interesting way to send data from an application to another application by using this other protocol there, like kind of fly under the radar of anyone who's just looking for IP data. Or we can actually make our own protocol. Like we can use socket and say we're going to have a custom packet. And when we want to drop data onto the network, we're going to bypass the transport layer and all the stuff below, and we're just going to dump the data right in there. So sockets are really, really powerful from that level. We can also say that it's going to be a stream-oriented or a datagram-oriented connection, and we can do that with more information here from the socket API. Then, if we take a look down a little bit further, and we'll do that here, let's go ahead and open up that as a new tab. So then the next thing we're going to take a look at here is some instructions that they give you in the manual page. This is just the man page for the socket API. And we see that we have to create a socket, we have to do the connect, the bind, the listen, and accept. We've done all of that. We could also do a socket pair. So socket pair, if you've taken operating systems, we had talked about named pipes. This is the way that we can actually use socket pair and use the built-in Unix named pipes as sockets. If you haven't had operating systems, don't worry about it. Even if you have had operating systems, don't worry about it. I've never used that function call in my life. We've seen the send message or the send receive from send to. We've seen that pair of things. So that's all pretty nice. The thing that you're going to end up really having to deal with as a network engineer is helping people through two different sets of problems. The first one is, and I'm going to skip ahead down here to where it talks about this p-read and p-write, or it talks about non-blocking I/O. So the first problem that application developers get into is they send data out and then they wait for that to finish, like they call the write system call. Write is going to wait until that socket has been sent and then the reply has been received. And then it's going to send the next batch of data, and then it's going to wait for that and it's going to be one thing after another. And that kind of defeats the optimizations that we're going to see later on in Chapter 4 when we look at TCP, Chapter 3 in a deep dive into TCP. where TCP can handle big gobs of data with lots of outstanding responses. And so one way to optimize that is to just use non-blocking I/O. And what we're going to do in this case is we're going to send, 5 or 6 or 10 or 100 or 1,000 packets of data, and then we're going to get error messages once we start overflowing buffers and things like that. So it's a lot more complicated to do, but it's a lot faster and a lot more optimized for the operating system's interaction with the remote host. So from that perspective, we probably want to at least understand that that's an option, and maybe sit down and instead of actually writing the code for your software engineer friend, you can just say, "Have you tried non-blocking I/O?" And that's probably enough to scare them away, and they'll never come back and ask you any more questions. But you may have to do some non-blocking I/O. The other, and I've had to do that, like for real, I've had to do that. The other pair of things here are these socket options. And the socket options are really, really, really magical. Like, this is our like unearthed arcana, and yeah, that's a good D&D reference right there. They say that they're documented, but oh, here they are. So here's the socket options, and there's just a bunch of these things. And you can go through the socket options, and every operating system is going to have its own really special set of socket options. So when you go to create a socket, after you create the socket, then you can go through here and do these special socket options. And I'm not going to go through all of them, but we'll just kind of talk briefly about what these things are. So accept connections is basically what listen does. So when we say listen, we're telling it, yep, I'm going to listen for incoming connections. If you have a machine that has a whole bunch of different internet or Ethernet devices or interfaces to a network, we might only want to bind a socket to one or two of those, or however many of those. And so you can use this option, bind to device, to say this socket is connected to this interface and only this interface. And again, we might want to do that to exclude other interfaces. So for example, if I have a really high-speed fiber optic connection to my server and I have an Ethernet connection to my server, maybe the application should not use the Ethernet for anything, but only use that fiber optic connection. If that's the case, then I would want to have the software developer add the socket option, bind to that particular device. This is a broadcast flag, and so what we do is we turn this on, and then everything we send out goes to everybody. And so that can be really useful if we're trying to broadcast messages out and say, hey, is there anybody out there? I don't know where the server is. Identify yourself. This was a bug that was in older Linux kernels. It shouldn't even be there anymore. This is for socket debugging. This is going to allow you to read all the packets that are coming in, and that's why it has to be run with root. So we can actually use this to debug communications over all sockets. This is going to allow you to bind a socket to one particular protocol. For instance, maybe instead of using the version 4 of IP, we want to use the new version 6 of IP only. And so, it retrieves that. So it'll tell you what what family you're using. There's another one that allows you to set that. If there have been errors on the socket, we can get those error messages. If we don't want to send data remotely, we can turn on the don't route. And so this is going to say, unless you're talking to another computer on the same LAN segment, don't talk to it. So keep alive, this allows you to have the TCP connection periodically send a ping message, and it basically just says, hey, are you there? And then the remote side responds with the keep alive message. And that way you know that the other side hasn't gone away. So you can use that if you have a connection that needs to be like established and stay established, but not constantly sending data, you can use this to keep them communicating. So linger allows the packet to kind of linger around after the socket's been closed. And so what we want to make sure is I don't get sockets coming back in or messages coming back in from a remote machine to a newly created socket. I really want to let this connection linger around to make sure that it's kind of sucked in any stray messages. Again, just for security reasons. So mark, we're going to mark each packet that's sent through this socket with a special signal or a tag, and then that can be used to be picked up by firewall utilities to say, oh, this packet should bypass the normal firewall rule because it has this mark set in it. We can send data as what's called out of band. So normally when we do reads and writes, we don't get any additional out of band data. In this case, we can ask that the out of band data is inserted into our main channel. Otherwise, there's another channel that we can use. We can get access to the out of band channel, so then we can send and receive messages that are urgent as well as messages that are just regular. We'll talk about urgency later on in chapter 3. This one I've never seen before. I think this is not related to internet access, but rather local pipes. Same thing here. Priority. So we can set priority. This is really interesting. In IP version 6, we're going to find that as a sending machine, you can set the priority that you're asking for. It doesn't mean you'll get it, but you can at least ask for it. And so that's really nice. We can set the protocol. And so this is going to be one of those read-only things again. This is one of the big ones. There's going to be a transmit buff size as well. This is the maximum size of memory that you can hold data from the network stack. And in my experience, this one right here is probably the most important for performance reasons with an application developer. So let's say that I know that every time the server replies with a message, like Oracle, for instance, is a really good example of this. If Oracle has a receive buffer that's too small, then what's going to happen is when I send data from the server back to respond to a query, it's going to be fragmented into 1,000 little packets. On the other hand, if I know that I'm on a local network, I know that I might as well go ahead and handle huge messages. What we can do is we can set the maximum receives buffer so that I can receive things as big as possible. And so you don't want to make them too big because when you allocate this memory, it allocates a lot of memory. So you might want to make it like the size of your message, or size of 8 or 10 messages, or whatever the thing is. You can experiment with how big it needs to be, but you really want to have this tuned to your application, and there's always going to be a performance curve where you get better performance from an application by tuning this receive buff. Timeout. So remember when we did the thing with the TCP example and it wasn't responding, it wasn't giving me an error? We can set the timeout message to make it like send a message and wait for 2 seconds or 10 seconds or 100 seconds or whatever the result is. Send buff. So this is the opposite of the receive buff, like I had said. So you want to make this as large as it is to hold the messages from your application. And what that allows you to do is write a gigantic message to this buffer and then let the operating system's TCP kernel send it out as optimally as possible. So instead of sending out like 50,000 different tiny messages, maybe the operating system knows something about the remote site and it can deliver it as one huge message. Let the operating system have this optimization and it'll be your friend. It'll do really well for you. So again, those are the two, receive buff and send buff, that are crucial to being able to get good performance. And what they're saying here is that there are some maximum values that your operating system has defined. So if I were to take a look at my operating system here, I'm going to slide here. So it says if I read this file, cat proc sysnet core wmem default, and by default I get 212K of memory per socket. And let's take a look at max. And that's also my max. So if we wanted to, as root, for instance, what I can do is sudo echo, I don't know, let's make it 212.922.0 to that file. And I can't do it because I'm on a Windows machine. Like, this is a virtual machine. But normally I'd be able to change the maximum amount of memory, and then I can change the default, and then I could make it be whatever I wanted it to be. So again, this is where, as a network administrator, you might have to work with both the software person to set this option in their program, and then also work with whoever's running the server to be able to enforce these limits or make them possible. And in fact, there is a file, well, there was a file, I had to go find it, that sets all of these limit files for you. And so those are the bulk of the options. I'm sure there's more that are like really kind of specific, and we kind of blew through them, but really ultimately it's those two. There's also a bunch of files that you can read, and they kind of describe some of those for you here as well. All right, so don't be afraid to mess around with some of these socket options. And you know, I wouldn't expect you to be able to like spew this detail out on an exam, but just understand that they're there, and it can really make your role as a network administrator or network engineer be a lot more useful when you can help the software people use your network more efficiently, or help the operating system people configure their machine to your network even better. And then likewise be able to use tools like Wireshark to look at how an application is using your network and make some suggestions. And then knowing how to implement those suggestions becomes like the gold in the mine. And so in this case, the socket options is really the way to go. So there's no way I could do anything like with a short lecture. I mean, we could spend a whole semester on socket programming. I don't need you to become good socket programmers. I just want you to know that um, these APIs exist, and that developers will be using them. And so when a developer talks to you about the connect system call is failing, you know what they're talking about, right?
Throughout the previous segments, we learned about the Sockets API. The next segment is from a network engineer at Red Hat and presents some of the system-level APIs and tools that can be used to diagnose and improve performance of a network. I have 2 points to make before sending you loose on that video. Number one, you may feel overwhelmed by some of the specifics of this video, and that's not my intent. Just focus on the fact that these tools exist, and that, if needed, you can pull them out of your toolbox in the future. And number two, this gets way more difficult on virtual machines where we don't actually get physical network cards for tuning. And so with those two kind of caveats ahead of us, let's go ahead and watch this interesting video from Red Hat and just kind of absorb the spirit of what this gentleman is saying, and if nothing else, enjoy his really nice Australian accent.